Good afternoon. My name is Jasmina Yolanda Vecino Yepes, and together with my colleague Carlos Alberto Leones Rivera and Vanessa Fontalvo Renix, we are pleased to present our research entitled Early Detection of Acute Myocardial Infarction, AMI, risks, using optimized machine learning models. We appreciate the opportunity to share our work in this academic forum. Introduction. Cardiovascular diseases remain the leading cause of death worldwide, accounting for approximately 32% of all global fatalities. Among them, acute myocardial infarctions, AMI, stands out due to its severity, high incidence, and rapid progression, often leading to serious complications if not diagnosed promptly. Traditional diagnostics methods, although widely used, present limitations related to clinical subjectivity, the use of invasive procedures, and potential delays in medical response. In light of this challenge, our study proposes an alternative approach based on machine learning techniques aimed at anticipating risks before the onset of critical symptoms, thereby enabling earlier and more effective medical interventions. To identify the most effective predictive approach, we conducted a comparative evaluation of 8 machine learning algorithms: random forest, support vector machines, gradient boosting, nearest neighbors, naive Bayes, decision tree, logistic regression, and AdaBoost. These models were trained and validated using the well-established UCI heart disease dataset from the University of California, Irvine, widely recognized in clinical computational research. This methodology involved a thorough preprocessing pipeline, which include outliers detection and removal, transformation of categorical variables through nominal and ordinal encoding, and hybrid imputation techniques that combine the accuracy of random forests with the simplicity of nearest neighbors. Additionally, grid search was employed to fine-tune hyperparameters and select the most relevant features, maximizing each model's performance. Now, related work. Several studies have explored the application of machine learning to predict acute myocardial infarction, addressing various models, methodologies, and clinical challenges. In the Netherlands, Saleh and his team, affiliated with the Dutch Primary Cardiovascular Care Systems, developed random forest models to predict both AMI and ischemic heart disease. Their results showed superior performance in terms of accuracy, sensitivity, specificity compared to the traditional SMART algorithm. In Sweden, also the Caprets and researchers from the University of Gothenburg apply logistic regression and artificial neural networks to emergency patients presenting with the chest pain. Their study demonstrated that incorporating demographic data, electrocardiograms, and blood test results significantly enhances the prediction of AMI and 3-day mortality. In China, Li and colleagues associated with the university hospital setting compared 7 machine learning algorithms to estimate the risk of heart failure following an infarction, with XGBoost emerging as the best performing model. And finally, during the 15th International Conference on Innovations in Information Technology, Mia, Mahmoud, and collaborators, researchers from the academic community in Bangladesh, conducted a comparative analysis of 6 algorithms. Once again, XGBoost proves to be the most accurate model for myocardial infarction prediction.
Let's continue with the data preprocessing and dataset overview. We use the University of California Irvine Heart Disease Dataset, which consists of 920 samples and 16 features. It includes demographic, clinical, and test-related indicators critical for evaluating heart disease and predicting AMI risk. Some of the most relevant variables were age, cholesterol level, blood pressure, the stress test depression, and thallium stress results, which played a key role in feature selection and model performance. During preprocessing, we applied several techniques to improve data integrity and model stability. First, we handled missing values found in the number of major vessels, color by fluoroscopy, and thalassemia test result variables using two advanced imputation methods. KNN with a K equals 5 and Euclidean distance, random forest imputation, which preserve feature relationships more effectively. Both approaches were tuned to match dataset characteristics. Then we performed categorical variable encoding using a hybrid strategy, nominal encoding for unordered variables like sex and chest pain type, and ordinal encoding for variables like slope of the peak exercise, stress test segment, and resting electrocardiographic results and fasting blood sugar. To address outliers, we use the set-score method, removing values beyond plus or minus 3 standard deviations from variables like age, cholesterol, and blood pressure. Finally, we apply a set-score normalization to standardize numerical features and ensure balanced model inputs. Let's now move into the model selection and tuning. We implemented and optimized 8 machine learning models, algorithms: random forest, KNN, logistic regression, decision tree, support vector machine, naive Bayes, gradient boosting, and AdaBoost. Model selection and tuning involve hyperparameter optimization using grid search, which tested 10 to 50 parameter combinations per model. Five-fold cross-validation is used to improve generalizability and reduce overfitting during training. We evaluated models using standard metrics for classification scenarios, accuracy, precision, recall, and F1 score to ensure a comprehensive performance comparison. Model performance was compared across the two imputation strategies, KNN and random forest, as both had different effects on data quality and final outputs. Here we have the methodology overview. The entire workflow is illustrated in our methodology overview diagram, which outlines each stage from data upload and processing to final evaluation. The full code implementation is also available on Kaggle to support transparency and reproducibility.
Moving on to the results and discussion from our exploratory data analysis, several important patterns emerged. We observed a gender imbalance with more male than female patients represented in the dataset. Additionally, most individuals had normal fasting blood sugar levels, and a flat slope of peak exercise was commonly reported. There was also a high occurrence of exercise-induced angina, which is clinically significant. Notable ST depression and thallium stress test results stood out as strong indicators of disease presence, making them essential for accurate prediction. These features guided our model selection and contributed to performance improvements. Regarding data preprocessing and distribution, we applied techniques such as outlier removal, Z-score normalization, and hybrid imputation methods, KNN and random forest, to enhance data stability and ensure consistent model performance. One critical challenge we addressed was a slight class imbalance, with a higher number of patients not diagnosed with AMI. This had implications for model learning, particularly in preserving recall and precision for positive cases. Lastly, from our feature relevance analysis, clinical variables like cholesterol level, maximum heart rate, resting electrocardiographic results, and again, ST depression and thallium stress emerge as the most predictive indicators for AMI. Their distributions not only inform our understanding of the dataset, but also validated the clinical relevance of our chosen features. These insights from data exploration and preprocessing were fundamental in shaping the performance and reliability of our machine learning models. Our comparative analysis highlighted two top-performing models: random forest, which achieved the highest accuracy of 68%, and gradient boosting, which has a strong generalization with the second-best results. While gradient boosting slightly outperforms random forest in terms of F1 score, random forest is considered the best overall due to its consistent performance across all metrics. Its superior handling of missing data using random forest imputation and its reproducibility. Therefore, gradient boosting is positioned as the second best model, showing strong generalization capabilities. Models like Naive Bayes, on the other hand, had poor performance, with accuracy dropping to 46%, indicating their limitations in handling complex non-linear patterns. Support vector machines and logistic regression present moderate results. Notably, random forest with random forest imputation consistently outperform all other combinations across all metrics. To conclude, our findings demonstrate that random forest, with its own imputation method, is the most robust setup for AMI prediction in our study. Ensemble models, in general, show promising results for clinical decision support, and data preprocessing strategies, particularly the choice of imputation, significantly affect model outcomes. For future work, we aim to explore additional feature engineering techniques and more robust preprocessing pipelines to further enhance performance and generalizability in real-world clinical settings. Thank you very much.